going to go ahead and take a look at number 61 from section 3.5, rational functions. So the goal for 61 is to go ahead and graph the following rational function. G of x is equal to x squared minus x minus 2 all over x squared minus 4x plus 3. One of the first things that we would want to do is see if we can reduce this rational function down. If we can reduce it down, that potentially will make our calculations a little bit easier and therefore more efficient. So what I would go ahead and do is pause the video and see if you can exercise your factoring skills to see if you can factor this down, to see if any factors will actually reduce it themselves out. So if you were to factor the numerator, we would get x minus 2 times x plus 1. And if you factor the denominator, we'll get x minus 3 times x minus 1. Notice that in this situation there are no factors that we can cancel out. You may be tempted to get rid of the x plus 1 and the x minus 1, but note that the operation between your x and your 1 is different. Since they are not identical, we cannot reduce them out. So in this case, even though we did spend some time factoring in order to reduce it, this work that we have is still useful. Okay? So before we begin, make sure that you have either a sheet of graph paper out or you've etched in a fairly accurate coordinate plane for yourself. Okay. So first off, we're going to go ahead and see if we can find any vertical asymptotes. To find our vertical asymptotes, we're going to focus on what restrictions our rational function would have. But again, notice that we've already started to factor this. So I'm going to use our factored form. And remember, to find our restrictions, we set our denominator equal to 0. So because of our zero product property, that allows us to then break this up into two problems. So x minus 3 could be 0, or x minus 1 could be equal to 0. The whole reasoning behind that is if their product or multiplication equals 0, then one of these mystery numbers must be equal to 0. If we solve this, we get x is equal to 3, or x is equal to 1. So that means that we have a vertical asymptote at x is equal to 1, and also another one at x is equal to 3. Note that in this situation, you're actually exercising previous skills that you have picked up for how to graph vertical and horizontal lines. Basically, your asymptotes are these invisible horizontal and vertical lines that you're making yourself aware of when you're graphing rational functions. So now we will go ahead and take a look at the horizontal asymptotes. And note that the information for your horizontal asymptote will come from the degrees located in your numerator and denominator of each of these polynomials that you have been presented. So notice that the degrees are identical. So the top in the numerator is 2, and the bottom, or the denominator, is 2 as well. So we will, to find the horizontal asymptote, we will take a look at the coefficients on the lead terms, and we'll create a ratio using them. So we would get 1 over 1 in this case, which is just 1. So that means that we have a horizontal asymptote at y is equal to 1. The next thing that we're going to go ahead and do is we will look for x-intercepts. And note that the general structure for an x-intercept, the coordinate point specifically, is going to be x and 0. So your y value will always be equal to 0 when you're looking for an x-intercept. So we will take 0 and we will equal that to, again, I'm going to utilize the work that we had previously, and I'm going to use the factored form. This is the same thing as our original problem, we just factored it. What I can do to save myself some time is I can represent the left-hand side as a ratio. So in other words, how can I write 0 as a fraction? 0 over 1. This permits me to treat this problem like a proportion, so I can quickly and efficiently solve the problem. 0 times what I have in the denominator will just be 0, and 1 times what I have in the numerator will just be the numerator. Notice that because we've already factored it, we are allowed to jump right into our zero product property. If these two values, when multiplied together, equals 0, then we can say that x minus 2 could be equal to 0, or x plus 1 could be equal to 0. if we solve this, then we would get x is equal to positive 2 and x is equal to negative 1. So we have one x-intercept at point 2, 0 and another x-intercept at point negative 1, 0. So we'll go ahead and plot those in. The next thing that we're going to do is we will try and locate the y-intercept. And again, the general structure for a y-intercept is going to be the x values will be equal to 0 and y will take on some value that we will find out. So to find the y-intercept, we will go ahead and plug in 0 for all of our x values. This results in negative 2 over 3. So we have a y-intercept at 0, negative 2/3. So that is going to be located about here. So we can go ahead and start connecting these points and see what we'll result with. So again, notice that what we had discussed prior is that the nature of this function is that it's going to want to get close to the asymptote. In this case, it will get close to that horizontal asymptote of y equals 1. It will connect through the x-intercept, the y-intercept, and then it will continue to get closer and closer to the vertical asymptote at x is equal to 1. Now the rest of this is a little bit more tricky, and it's basically just because we don't have as many clues as to how the function is going to react. So this is where you can default to using your technology or your calculator to help you. I'm going to go ahead and generate a quick table for you by hand, just to show you where this thought process is coming from and so that we don't just black box this information. You will want to pick certain values, so it looks like we've already taken care of all the x values going from negative infinity up to that x is equal to 1. So I'm going to work with 3/2 or 1.5, 5/2 or 2.5. In other words, I'm going to pick values that on the left and the right of that other x-intercept that we found. And then I'm going to pick a value like 4. So I want to know what's going to happen right after our x value or our asymptote that's situated on x is equal to 3. Okay, so I would suggest using your technology to help you with this to move you along. I will demonstrate how to find this first coordinate point, and the others I'm just going to fill in. You would need to do this either, again, using your calculator, or I would suggest taking the time and try to do it by hand. Exercise those skills to make sure that you don't get rusty. So if we were to go ahead and plug 3/2 in for x, or you could also use the decimal equivalent, but fractions are inevitable, like death and taxes, I suppose, so why not face the beast? Okay. So if we were to evaluate this, 3/2 squared is the same thing as 9/4 minus 3/2 minus 2. Again, 3/2 squared is the same thing as 9/4. If we were to take care of this multiplication in the middle term, the 4 and the 2 will cross cancel, and that will leave you with negative 2 times 3, so that gives us negative 6. Now I'm going to write everything so that the numerator has a common denominator and the denominator has a common denominator as well. I know that sounded kind of funny. So 9/4 minus, I'm going to multiply the top and the bottom of 3/2 by 2 to get 6/4. And I'm going to multiply the top and the bottom of this 2, in other words, I have a 2 over 1, by a 4 to give me negative 8/4. We can apply that same logic to what's going on in the denominator overall. So negative 24 over 4 is the same thing as negative 6, and 12 over 4 is the same thing as 3. If we continue to evaluate this, simplify what's going on in the numerator, that is going to give us negative 5/4. And then if we simplify the bottom portion, or the denominator, that is going to give us negative 3/4. So from here, we can take this division problem that you're seeing, this complex fraction, and turn it into a division problem that we're used to looking at. So this would be negative 5/4 divided by negative 3/4, which then we can say, let's skip the first fraction, flip or take the reciprocal of the other fraction, and then do a multiplication. The 4's will cross cancel. A negative times a negative will make it positive, and this gives us positive 5/3. If we were to continue in this fashion, 5/2 would result in negative 7/3 as our output, and if we put 4 into our function, then we would get positive 10/3. So if we were to plot these points, let's see, 1.5, 5/3. 5/3 is equivalent to about 1 and 2, well, not about, 5/3 is equivalent to 1 and 2/3, or approximately 1.6 repeating. So that's going to be around here. And then our 5/2 are 2.5. And then we need to locate negative 7/3 on the y-axis. Negative 7/3 is equivalent to negative 2 1/3, or in other words, negative 2.3 repeating. So that is going to be about here. And then our 4 and 10/3. 10/3 is 3 1/3, or 3.3 repeating. So that's about here. And now we can use this information in order to plot. Okay, we're going to get really close, connect, and then go through. And close to the asymptote, cut through that point, and then get back close to that horizontal asymptote. Now let me take a moment to explain. Notice that the middle one, the middle portion of this function, it is cutting through the horizontal asymptote. Please understand that it's the vertical asymptotes that are very strict. You are not able to touch or cross the vertical asymptotes at all. You can just get close. Horizontal asymptotes are a little bit more, I guess, loose in certain terms. So that's why it does pay to kind of check by using your calculator and also by checking certain points by hand. Basically, it's because the horizontal asymptotes don't face as many restrictions as you would see with the vertical asymptotes. Recall that when you're finding the vertical asymptotes, you're also finding restrictions. You're finding points or x values in the domain that cannot work in your function. They never will. So that's why vertical asymptotes are much more strict than your horizontal asymptotes. Okay, and then notice here, even though I only plotted 1 point in the final section, here I'll circle it in yellow to let you know what I'm referring to. I only plotted 1 point to know where the function was going to exist. If you wish to plot a few more points or check using your calculator, by all means go ahead and do that. But your final solution is what I have kind of boxed in aqua. This is what your graph will look like. I hope that that was clear. If you have any other questions, please feel free to come and see me.